Okay, there we go. All right, so today we are going into talking about developing probability theory. So you've probably all had a class in statistics or probability where you had to calculate the probability that, I don't know, if there's a bunch of marbles in a bowl, what's the probability given this number of each that you'll get a red one? Okay, so you've probably taken one of those classes, and I will say in general, Blaise Pascal gets a lot of credit for creating or founding, if you will, the branch of mathematics that is known as probability, and a little bit of statistics, but mostly probability. We've talked just a tiny bit about the development of algebra, the development of calculus, and we would probably be remiss if we don't talk a little bit about the development of probability. So Blaise Pascal, let's see, his dates, I'm going to talk a tiny bit about other stuff before I get there. His dates are 1623 to 1662. And he's considered one of the co-founders of probability. Okay, we'll get to the other guy later. Probably mostly we'll talk about Blaise Pascal today. Okay, and you've probably heard the name Blaise Pascal before. There's a programming language called Pascal. There's Pascal's triangle. There's several things that he is kind of attributed to. He didn't write the programming language. It's just like basically named after Pascal. We'll talk about that. Why? But let's talk first about probability theory in general. What is probability? Like anybody that's taken a probability class, what is that based on? What are some of the things that you think probably helped to come about the idea of finding a probability? Nobody's going to answer. What are some of the things you do? I mentioned marbles, but what else? You do cards, right? And dice. Probability comes in a lot for things like life expectancy, mortality rates, things like that. So it's philosophized, I guess, that probability started out with a need for talking about wagering. Of course, they didn't call it probabilities back then, but...
The founder of probability didn't make the life expectancy. Lived to 39.
He died young. That is actually a really good observation. We'll talk about that. But yeah, 39. So he did not make the life expectancy that you would think. And people did die younger back then in 1662, but not normally 39, right? That's still pretty stinking young. So exactly, we will, in fact, I'll just throw that out there. Blaise Pascal is known as the could have been mathematician. Okay, so he's the greatest could have been mathematician. If only he'd lived longer, if only he had just focused in on the math, because we'll find out he's kind of all over the place. If only, if only. And you can tell there's a lot of really great genius going on in the background of him, but he doesn't live long enough to live up to it, basically. So the could have been mathematician. Really young. Okay, wagering probabilities, that's a lot. Gambling is not new, let's put it that way. There's evidence of people playing games and cards and different things for wagers as far back as the Egyptians. Okay, so like talking 2500 BC, there was a game called Hounds and Jackals. That's what it was called. I have to pull that one out of my head. 2500 BC in Egypt. And here we are in 1600s, right, AD. So, but people were wagering things and money and whatever on games of chance, basically. Okay. We have the development of cards. as an actual set of cards, and that happened, let me see when that happened, sometime around, they think, the Middle Ages maybe, into the Renaissance. So, did you know, this is an interesting little factoid, that originally the faces of the kings, nowadays whenever you look at a deck of cards, the faces of the kings are kind of generic and stylized or whatever, but originally they were developed and they had actual kings on them, like King David from the Christian religion, right? And so it would be like a portrait of him. And then there would be like Julius Caesar was one of the kings to represent the Romans, right? The empire there and that kind of thing. I think Charlemagne was one of them. I'm trying to think who else. But there were kings on the cards. So those were developed, they think, sometime around the Middle Ages and into the Renaissance, because it said that games of chance were used to basically keep the knights from being bored, okay, keep the soldiers from sitting around being bored. So we know that they were developing cards by then. But clearly, the ancient Chinese people had games of chance and stuff like that, different bones, different dice, things like that they would wager on. Okay, so that's one of the things. And then I heard also life expectancy or mortality rates. Okay, that's definitely one of the things that we would be looking at. This would be a statistical analysis, right? Looking at people's life and death, and we're going to actually see a really early version of that and how that came about. Also, the precursors for statistical data would have been things like inventories or census data. Okay, and if you think about it, way back in the Bible times, they made people go to Jerusalem to be counted, right? Okay, that's the whole premise of the Christmas story, right? They had to go and be counted. We know that the Roman Empire kept really close tabs on who they had as, quote, citizens, because they wanted to tax them, right? Okay, so that was a big thing for the Roman Empire. So census data and stuff like that, starting to keep track of that, kind of almost in itself leads to looking at mortality rates, right? Because we want to know, oh, that person's not a citizen anymore, I can't tax them, that kind of stuff. So we start seeing these kinds of data being collected, and that's some of the earliest statistical things that we look at, actually. Okay. What we see here is this is one of those situations where the data was there. We were already doing stuff like gathering census data and things like that, and then later the math theory comes to kind of go with it. So we have a couple of people that are not necessarily people that we care about for mathematicians, but they kind of contribute to our story. So one of the things is we want insurance, okay? So there's a merchant. And when we talk about probability, we're looking at the probability that something will or won't happen, right? So the certainty of an event or whatever. And so there are merchants with vessels, ships and stuff like that, and they want insurance. Okay? So what's the probability that I'm going to stick my ship out on the water and there's going to be a huge storm and comes and knocks it down, or that I'm going to be have pirates attack me and I'm going to lose all my whatever my cargo is? I might need insurance. And actually we see there's a company, Lloyd's of London. Anybody heard of them before? They're still in existence. They were founded around 1688. They're an insurance company. Okay, 1688, we're getting insurance. And so they're not going to insure a vessel, for instance, that's going out into the water, the open seas during hurricane season, right? Because they know you're likely to hit a hurricane. So they want to know those probabilities, and that's where we're going to see some of our probability theory coming in. So there's this guy named John Graunt. Graunt. 1620 to 1674. And he is not a mathematician. He's a merchant. Okay, but he does have vessels, and he does want them insured, and he does want to know what's the probability that his men are going to make it home alive, basically. So in 1662, he publishes something called Natural and Political Observations. Natural and Political Observations made upon the bills of mortality. Bills of mortality. Kind of a long, lengthy name. I'm sure it was written in the common language, not in Latin or anything like that, because this guy wanted to actually use this, not for it to be it's not meant to be a scholarly publication, right? So, bills of mortality, basically what we're looking at is keeping up with information on the number of deaths in the different areas of England. So, they call them parishes instead of counties, but it's a similar thing. So he would go around and find out, okay, how many people are dying, how much this, how much that. And it's actually kind of interesting because he wrote this up, and in it he poses a question. Page 442. He poses a question and he says, how many people die early, like before a certain age, young kids getting things like influenza or whatever that just, it kills them early, and they don't make it past. He picked the age of 6. How many people die early, and how many people don't make it past a certain age? Okay, and he picked 75 as his age. So he poses 2 questions in this bill. He's gathered all this information. So how many die early? How many don't make it past a certain age? And both of these are really interesting questions, right? We want to know how many children are going to die approximately. Like if you have a kid, what's the probability that your child will live to be an adult? And then we want to know, you know, like you said, what's the average life expectancy? Am I expected to live till 80 years old? Back then you weren't, but now with medical advances and stuff, lots of people live to 80 years old, right? So it just depends on the age you're in. So this is one of the things that he put together is this table. I'll show you right here. And this is what he says. Ages on the left, survivors on the right. Age of 0. Well, that's like just how many are being born, right? So 100 people. And it's, of course, interesting to us maybe whenever we look at probability, we do a lot of proportions, a lot of percentages, things like that, and a percentage is always out of 100. So it's interesting to me that he picked 100 people. So he goes through, he had a lot more data than 100, but he said per 100, okay, only 64 people are going to live to be 6 years old. That means 36 kids are dying out of each 100 that he was looking at in the different parishes around. And then he went basically by the decade after that. So 16, this would be probably considered barely about to be an adult back then. You know, this is about the time that people would be thinking about getting married. Only 40 people are living until 16. That means what? 60 people have died by the time they're 16. So that's a lot of mortality going on there. Living to 46, only 10 of the 100. Wow. okay, I'd be dead by now. Okay, I'm serious. 56, only 6. 66, only 3. And people over 75 years old, only 1 per 100, which means 99 out of 100 people die before they're 75, or by the age of 75, let's say. Okay, in this time period that he's at. Okay, of course we know our numbers are much different right now. We don't have as many children dying young. We've put in a lot of things that medically speaking help extend people's lifetimes. So this would not be our table right now, but basically this is a really early mortality table. And he went so far as to interview people and try to find out not just who died and when they died. They did have gender, okay, females and males, but before his time, that's about all they had, okay, gender and maybe an age, but probably not. So, and they had, before this, gender, and they had, was it a disease that killed them or an accident? Which I find interesting in that too, because it means that they're not really thinking that people are dying of old age, right? Okay, you're probably dying in some kind of, I don't know, maybe a farming accident or something like that before this. So he wanted to know some stuff, okay? He wanted to know specific causes, and he wanted to know ages. Okay, because he's actually looking at the mortality rate and when people die. Okay, so this guy, he's an interesting person. He puts out some interesting data for us, and the reason we care about him is because at some point he actually writes to Blaise Pascal. Okay, around this time, Blaise Pascal's still alive. He writes to Pascal and asks for help. Basically interpreting his data. He has a lot of data and he needs some help interpreting his data. Okay, so this is where Pascal kind of comes in, and we'll get a little backstory on him and his life. But this guy Grant is basically the one that just pulls him in and sucks him into this whole story and says, okay, I need help. What we're going to see is he actually had other things on his mind other than probability, and because of Grant, he actually kind of becomes one of the founders of probability. So if it wasn't for this guy, we might not have all of what we have now. I'm sure it would have come, but maybe not quite so soon. Okay. There's some other people that are looking at stuff like this, a couple of brothers in Holland and different people, but this one is the one we care about because he's the one that dragged Pascal in. Okay. I talked about that. Okay. Let's look at, there's one other. Oh, of course, we got to talk about him. Cardano has already written the book called Liber de Ludo Allier. I do not have a translation for that one, sorry. It was written in 1550. But he didn't publish it, and it was actually found after his death. And they published it. And I don't know why he didn't publish it. It would be interesting. It wasn't printed until 1663, which is actually after Blaise Pascal's death. So we know that he didn't use any of his stuff. But the nice thing about it is Cardano, in his works, he's looking at stuff and he's talking about probability as a ratio. Okay. So the probability that an event is going to happen. Now his math is actually not quite right. It's actually interesting because, and if you read through your book, they'll talk about 4 or 5 different instances of people who were trying to do math for probability and weren't quite getting it right. Okay, so they didn't quite get it right. But he did talk about probability of a ratio as a ratio, and he had a basic idea of the probability that something would happen should be the sum of the possible outcomes to get what you want. We'll call it the desired event. Sum of all the possible ways that you can get what you want divided by, and he called it the whole circuit, but we'll just say total outcomes because that's more what we would talk about today for probability. Okay. And he's actually pretty close because sometimes it is the sum, right? It depends on whether we're talking about independent events and dependent events and all kinds of other stuff going on in there. If it's an and situation or an or situation, sometimes it is, but we now know that sometimes it's not a sum at all, right? Sometimes it's just a multiplication and things like that. So I think that he was onto this. He was really close. He wanted to talk about card combinations. He talked about the possibility. He wrote an entire chapter on the possibility, different possibilities for tossing a die. Tossing a die. Okay. And in fact, I think he wrote a chapter on possibility of tossing a single die. And then I think he had another chapter that was on multiple dice. Okay, so he realized that there was a difference there. Card combinations for a particular game, similar to poker, that kind of thing. So he was in there doing a lot of stuff. And he's the one that actually told us and put it in writing that a die has equal chances per side. He said if it's an honest die, okay, and we would call it a fair die nowadays, but absolutely. Okay, so we have some of that stuff in there. Even Tartaglia dealt with a little bit of the probability theory. He knew that we were talking about portions, and he wrote a little paper on it way back in 1556. The thing with Tartaglia, though, is he actually got it wrong also. He's one of the ones that got it a little wrong. And we know he was a genius as far as math goes, but in his writings he says something to the effect of that he's having a problem comprehending it or something like that, that he can't quite suss out what needs to happen. So he thinks that the probability of an event happening is a judicial issue. Like, it depends, okay? It depends on this, it depends on that, which it does, but he said it's a judicial issue, it is not a mathematical issue. So he kind of just said, I can't figure it out, so I'm just going to say you can't do it, that kind of thing. So, kind of interesting. All right, enter Blaise Pascal. He's our guy. He's the one we care about. So in your notes for mathematicians, make sure you've got him marked off as somebody we want to know. He actually was a writer and a religious philosopher. And in fact, if you read some of the math history books, that's actually where the complaint comes in about him, is that his attentions were divided. There's a time period in his life of about 3 or 4 years, and like Jeff said, we don't really have a lot of years to deal with here, right? So he takes a break from mathematics. He actually turns his back on it. He says, I'm going to abandon that. It's not worth my time. Instead, I'm going to focus on my religious studies. So his attentions being divided actually causes him to have some issues, and we'll see that. He wrote really great prose in French literature. And in fact, if you are a literature major, English, that kind of thing, they claim him. Okay, so we claim him over here in math, but they claim him over there in English because they say, oh, you know, he wrote all this really great stuff. Again, He bounced around a lot from thing to thing, and so his life is a little divided. His mother died when he was 3. And his father took care of him and educated him. And that ends up being an interesting thing. His father was a judge by trade. And apparently pretty stinking rich, because at some point he decides that he's going to just quit work, basically, and move the family to Paris because he wants to focus on educating Blaise, because he's just apparently a very good student, and he's progressing to such a manner that his father thinks that he needs to just focus on his education. The father was also a mathematician by hobby. So it's interesting because he actually had, like, you would call it an education plan for Blaise, and in that he said he will not study mathematics until he's 15. I don't know why that is. If it was your hobby, you would think you would want to share that with your child, but I guess maybe he thought it would monopolize his time, I don't know. But he said no mathematics until 15, and actually what we'll see is that Blaise just had a natural curiosity for math, in particular geometry, and started doing it on his own, even though his father wasn't teaching him. So that's interesting to me. The problem with Blaise is that he has stomach pains his entire life and migraines throughout his life. So he's always ill, always ill. And I started to say frail. He's frail his entire life. So one of the theories is that maybe his dad didn't want him to study mathematics because he was worried that it would consume him and that he wouldn't have energy for other things. That's one of the theories. I don't know if that's true. Okay, we know for sure, though, that he was sick most of his life. Let's see. At 12, it said, his father came down and found him drawing, and I find this interesting, rods and rounds on the tile floor. Okay, he had like charcoal, basically, is the way that the story goes, and he was drawing things on the ground, rods and rounds, and we would call those lines and circles, but those were his names. He had named them because he hadn't studied any of this at all, and so he doesn't know the names for them, so he gave them something, rods and rounds, which kind of makes sense. Okay, so he's drawing this stuff on the tile floor, and his father goes, well, shoot, I guess if he's that interested in it, I should do something about it. So he gives him a copy of what? What do you think? Geometry. Euclid's Elements. Euclid's Elements. So he gives him a copy of Euclid's Elements for him to just read in your spare time, basically. Enjoy it, that kind of stuff. Rumor has it that Blaise actually came up with basically all 32 of the propositions that Euclid had on his own and was able to work through them at a very, very young age on his own, before 16, I believe is the date. So, yeah, really interested in that, which is cool. All right, here's the date. By 16, he wrote and published something called the Essai pour les coniques. Pourlesconiques. This was in 1640. Okay. He wrote it and he published it, and that's essay on the conics, right, is what that means. So it's all kinds of stuff about the circles and the ellipses and the parabolas and stuff like that. And he's writing this own thing for him. And they say that he had no fewer than 400 propositions. Now, they weren't proven, but they were propositions, things that he thought were true. I think these things are true about the geometry that I'm studying, basically. And this is at the age of 16. So that's pretty impressive. This was conic sections. Okay, he had stuff like tangents to a parabola, which we know that leads towards calculus, right? So he had really early statements for that, and everybody who read it loved it. Okay, they praised him, they put out really good words about this young protege. He's only 16, he's writing this stuff. Everyone except Descartes, which is interesting. And basically what Descartes said is that I cannot pretend to be interested in the works of a boy. He's too young. Who cares what he is doing? Okay, that's what Descartes said about that. Okay. At some point, his father he gets a government appointment, and that happens a lot whenever you're things like a judge and whatever, the royal governments can say, hey, we want you to do such and such. So the father is appointed basically as an accountant. This pen is done. But he's using his judge abilities to straighten out a tax situation. So what happens is this kind of sways, again, the course for Blaise Pascal's life, he just kind of bounces all over the place. He sees his father, and he sees that he's doing all this calculation work. And there's a lot of places with arithmetic where he's likely to make mistakes. And so he sees that, and his father's just slaving away over these number columns for hours and hours and hours every night. And he says there's got to be a better way. And so basically, he takes the idea of an adding machine and he makes it better. So he calls this thing a Pascaline. P-A-S-C-A-L-I-N-E. Pascaline or Pascaline, however you would say it. Okay. He creates this thing called a Pascaline, and it's similar to a desk calculator that you would see, and I've got a picture of one, I'll show it to you. Except for it's like an adding machine with gears and shafts. Gears and shafts. Okay, so page 452. This is also in your book. Page 452. It's kind of cool. So it looks like this. Okay. And basically what they said was it could add a column of up to 8 numbers. And if you look at them, it's got like 6 slots, so I assume they're pretty big numbers even. And using gears and shafts, there was the adding machine at the time basically used rods that had different multiplications and things like that on them, and you can manipulate them the way you wanted them to do your mathematics. And so this one did that, but it used the gears and the shafts to do the manipulating for you. So it's kind of like you could punch in 16 plus 12 plus 22 and that kind of thing, almost like what we would see in more modern adding machines. So kind of cool. The problem with it is that it had all these wheels and gears in it, and that those would wear out, and also they were expensive. So the cost of making it meant that not just anybody could have it. It was prohibitive. Okay, so that's what happened with that. And in fact, he makes this thing, and then he spends the next 10 years of his very short life, bless his heart, revising and editing this. Revising the Pascaline. And he really thought that this invention was going to get him some money, basically, and that's why we think he spent so much time on it. He had 50 different models with improvements and so on of this machine. And unfortunately, just a very few of them actually got sold, and it did not turn into the money maker that he had hoped it would be. 10 years he spent on that. Okay. So I mentioned earlier that there's a time period. This is still kind of mathy stuff, still kind of sciencey stuff. He's been doing that. And then he just suddenly comes into a moment where he says, I'm just done with this. I'm wasting my life. I should be doing more important things with it than mathematics. And so that's what happens. He has this, his father dies. That's part of the problem. And there's this time period, and your book calls it the profane period. It goes from 1651 to 1654, which is actually kind of getting close to the end of his life. He spends about 3 or 4 years first just kind of wasting away his life. He's in society, he's doing things, enjoying himself, because I guess he doesn't have any family ties anymore, that kind of thing, so he can just spend his money however he wants. So this is what he calls his profane period. And then right after it, in 1654, is when he just abandons math. He's going to do religious studies instead. He doesn't know that he only has about 8 years left to go. Okay, he does that. He becomes a critic of anything that's Jewish, basically, and then he kind of takes the time to write this book, if you will, that's an apology for the Christian religion. Okay, all the things that are wrong with, in particular, Jesuits. Okay, that particular branch of the Christian religion. And so he spends a lot of time doing that, and then just abandons that as well. So he's like, okay, I'm going to just abandon that as well. So in 1654, something interesting happens. This guy named Chevalier, it's probably like Chevalier de Maire, and you will actually see his name sometimes pop up in mathematical topics. He gets a little bit of credit. This guy is interesting, though, because he's not really a mathematician. He's making a living on gambling, in particular cards and dice. Okay? And because he's making his living this way, he wants to know. Okay? And they're betting on weird stuff. So basically, in 1654, he contacts Pascal and he says, what's the probability, and of course they're not necessarily saying probability, but what's the probability that I can roll, if I'm rolling 2 dice, okay, at the same time, that I can roll double 6s. Okay? And basically, it's like, what's the probability that I can keep on rolling and I'm never going to get a double 6? So it's that whole thing of you figure out what the probability of a double six is, and then you subtract it from 1, because he wants to actually know when is he not going to get one of those. So Pascal actually very quickly figures out for him, and y'all have probably all seen the tables before where you talk about rolling, when you're rolling 2 dice, if the first, this guy's just got to go. If the first number represents, say, a red die, and the second number represents, say, a blue die, then what's the probability that I'll roll a 1 on the red and a 1 on the blue? And then what's the probability that I'll roll a 1 on the red and a 2 on the blue? And what's the probability I'll roll a 1 on the red and a 3 on the blue, so on and so forth. And this basically turns into a 6x6 matrix. You've probably seen those before. There's one in your book if you want to see it. Blaze really quickly says, oh, the probability that you're going to roll double sixes is only 1 time out of 36 possible outcomes, right? So there's only 1 time out of 36 that you're going to get that. And so that means that 35 times out of 36 you're not getting the double six. So basically what the mayor was wanting to do was bet people that either he could not roll a double six, like keep on rolling and make sure you don't roll a double six, or that they would roll, the other person would roll a double six. Because if you know the probability of rolling a double six is only 1 out of 36, then hey, go ahead, I bet, go for it, and you can bet against them because your probability is 1 minus 1 over 36, which is 35 over 36 of not getting a double six. Okay, so he's trying to get this information, and Pascal actually gives him that pretty quickly, and then all of a sudden, it's 1654, he's interested in probability theory now. Okay, so he's just this bouncing around from topic to topic, and that's why he gets that name, the greatest could have been mathematician. Bless his heart. He didn't have enough time to bounce around from topic to topic. He should have just focused in on what was really interesting to him. But it's nice because, again, he's looking at probability, and he's looking at a little bit of statistics work, and that kind of captures him, and now we're going to get him back in math again, which is really cool. The other thing that happens from that is that Pascal, so it goes like this. Demir contacts Pascal and says, help me. And Pascal starts talking to Pierre de Fermat. Okay. And so there's kind of this 3-way communication thing that gets set up where Pascal and Fermat end up coming up with a lot of kind of interesting stuff about probability. Stop that. Coming up with a lot of interesting stuff about probability. And these 2 guys are the ones who get the credit for being the founders of probability theory. Probability. Goodness. You would think I could spell theory. Okay, so they end up corresponding a lot. It's actually interesting because we know for a fact that they're not the first ones who saw, we talked about it, right? There are other people who've already realized that probabilities are ratios and that we can look at the outcomes and the events and stuff like that. So they're certainly not the first one. We know actually that Chinese people had a lot of stuff really early, like around 1300 AD. So they were already looking at this stuff, but probably because they were putting stuff in writing and letters back and forth, probably because other people are approaching them for help, they get the credit. So they're the first to kind of write it and print it and stuff like that. Okay. All right. What else about him? He writes a book, Triangle Arithmetique. Again, it's written in the vernacular, so we're writing in French here, probably, would be my guess. which is the arithmetic of the triangle. Okay. This actually went out in 1654. Actually, I think it's not a book. I think they call it a treatise. So I think it's just like a paper. But he writes this guy, and in it, he kind of comes up with an explicit formula for combinations. How to find different combinations. What's the likelihood of this? What's the likelihood of that? And what we would call today, now he wrote in verbiage. He wrote it out in prose. He did not have the exact notation I'm about to use. So still no notation. Dang it. So he doesn't get credit for that. But he basically came up with this idea. N choose R. You guys have done that before, I'm sure. N choose R is N factorial over R factorial times N minus R factorial. So again, he doesn't have that lovely factorial notation, but he writes it out in words. He knows what this is. He has the idea for this is how we're going to find N choose R, which is awesome. If you have this many opportunities, how many ways are there for you to choose this many things out of that? Okay. 8 marbles. I want 2 of them. How many ways? Okay. What we need for this notation, which he doesn't have, is that factorial guy. And unfortunately for him, he doesn't have that. It will be developed, that notation, later. 1808, so it's after, of course, Pascal's death. And this is by some guy named Christian, Christian, Kramp, Kramp. So we get a lot of information from Pascal. He comes up with all of that notation, or all of that idea for how to calculate that, but it's one of those instances where the notation's just not there, and maybe he's not as good as Leibniz at picking out what that notation should look like. So we don't get that until a couple of hundred years later, basically. Okay. The other thing that is in his book, Triangle Arithmetic, is basically what we call Pascal's triangle. Okay, so we're going to take just a second to look at this, a couple of minutes, not too terribly long. We've probably all heard of this. Can we all reproduce Pascal's triangle? And do we know how? Without just memorizing it. And what does Pascal's triangle do for me? You don't know? Oh, yay, yay. That's all right, I like that, because that means we need to talk about it. Okay, so this comes up with, it comes up with the binomial expansion, basically, okay? So if you have x plus y squared, for instance, you know this is going to be 2xy, x squared plus 2xy plus y squared, right? Okay. So basically what Pascal's triangle does for us is it gives us the coefficients that go with that, okay? The 1, the 2, and the 1, okay? We have to know what's going on with the different variables and the exponents. So we have to know, for instance, because the binomial is squared here, that we're going to start with that every power will have a total power of 2. Does that make sense? Every term will have a total power of 2. So since I'm squaring it, I get x squared. I start out with the first variable, and it's raised to the second. The second term, I will subtract 1 from the x guy, and I will add 1 to the y guy. Well, the y guy was y to the 0, right? There wasn't 1 sitting there. So it was y to the 0. Now it's y to the first. The third term, I subtract 1 there, so the x goes to a 0, which we don't write. Okay, we know that that's a 1, so it's no big deal. And I add 1 to the y squared. So every time when I look at these exponents, the total of them will be a 2. Okay, and the same thing happens if I do x plus y to the third. Every time, every term that I look at, the total of the exponents adds up to a 3. And you just have to know that this one is decreasing by 1 each time, and the other one is increasing by 1 each time. So that's something that's left to you to know. But if you don't remember these coefficients, you don't have to, because Pascal's triangle tells us. So real quickly, let's do the third guy. It's going to be x to the third, and it's y to the 0, but I'm not going to write that. The second term, I'll come back with coefficients. Second term is going to be what? What, x?
X squared y.
Squared y, and we'll come back for the coefficient. The third term is going to be something x y squared, right? Because the x goes down by 1 and the y goes up by 1. And the last term is going to be something, and the x goes down by 1, so it's going to be a 0. The y goes up, it's a y to the third. Okay? So again, every time my sum for my exponents, my total exponents adds up per term to whatever the power was here. Okay? So that's the binomial expansion. It's really a kind of really handy thing if you're working through some of your algebra in a calculus class or something and you're like, something plus something cubed, I've got to cube that binomial. It comes in handy to just know how the exponents are going to look and then to know Pascal's triangle. So Pascal's triangle goes like this. You always start with a 1 on top. And then you're going to spread out on the diagonals is the way I think about it. Each row has one more term. So we start with 1 on the first row. The second row is going to have 2 terms, okay? And on the outside diagonals, I'm going to split off onto the diagonals. They're always going to be 1s. So the second row is a 1 and a 1, okay? And then the third row has 3 terms, and again, I'm going to have a 1 on the outside and a 1 on the outside because that outer diagonal is always a 1. But how do I find this middle guy? That's the question. Okay, you add the 2 terms immediately above left and right. Okay, so this term is in the middle, 1, 2, 3 for the third row. And Katie says, hey, look, add that guy to the left, add that guy to the right. 1 plus 1 is a 2. Okay. Okay, so this would be x plus y to the 0, x plus y to the first, x plus y squared. So think about that for just a second. Make sure everything lines up for us. Anything to the 0 is just a 1, right? So my coefficient is a 1. Anything to the first power is just that guy, so my coefficients are both 1s here, no problem. And by the way, if this was like 2x plus y, then I'd have to change my coefficients, right? So I would multiply through, but that's okay. Okay. Then I get, okay, x squared, that was a 1, we had that up there, plus 2xy, yep, we had that up there, good, and then plus 1 y cubed. Oh, we had that up there or y squared up there as well. Okay? So if we can just figure out how to make this pattern work for me every time, I'll know these coefficients for the x plus y to the third guy. That's the next row, right? Again, the first guy is always a 1, the last guy is always a 1, so you can go ahead and fill those in. I'm on the 4th row, so I know there should be 2 terms in here. Okay, and then it's just a matter of reapplying that pattern that we just heard a second ago from Katie. Okay, so what should this number be?
3.
Add them, 1 plus 2 is 3. Add these guys, you get a 3. Okay, so up here on my expanded x plus y to the third, this should be a 1, this should be a 3, this should be a 3, and this should be a 1. Okay. So it becomes very easy to do these expansions if you just know those 2 things, one about the exponents and one about Pascal's triangle. So real quickly, next row, 1 and a 1, This is the fifth row, so there should be 3 more terms in there, right? Total of 5. So figure those guys out. And then we'll figure out what's x plus y to the 4th real fast. We'll apply everything together and make sure we can do it all. This should be a 4. This should be a 6. This should be a 4, right? Okay. So to do x plus y to the 4th, this is going to be 1x to the 4th plus what? Oh, let me write it down. We can apply everything we know now. X to the 4th plus 4, because that's that coefficient, right? And then just figure out the exponents. This one's going to go down by 1, so it's x to the 3rd. And then the y goes up by 1, so y to the 1st. That adds up to 4. I'm good. Plus, the next term is 6. What happens with my variables? X squared, y squared, absolutely. Okay. And then the next term is a 4. X is going down by 1, so it's just going to be x. What about the y? Y to the 3rd. And the last term has a 1 for the coefficient. The x goes down by 1. X to the 0 is just a 1. We don't care about him. So the y becomes y to the 4th. I'm telling you, if you have ever multiplied out x plus y times x plus y times x plus y times x plus y, it takes a while to do it, right? And I've seen people like in the math lab actually trying to work that out, and I'm like, oh, there's such an easier way, you know, but you kind of have to have a bit of the math background to see it. I taught this in high school for algebra students. So you have to be able to see it, but once you see the patterns, it's actually really pretty easy to get that binomial expansion is what that's called, right? And again, we know people already had this triangle, okay? We know Pascal is not the first one. He gets the credit because he put his name on it, basically. He put it in print and put it out there, okay? Just real fast, there are some patterns inside of Pascal's triangle. So this is the primary usage that we have for Pascal's triangle, other than it's a really cool pattern thing that I can do with math education students and young school-age kids. But this is the main mathy thing there, so make sure you have a note for him somewhere. He gets the credit. All right, so cool patterns inside of Pascal's triangle. There's 2 things that I want to point out to you. One is that it is symmetric, which means if I split it right down the middle, it's the same on both sides, right? If I split it there, the 1 is reflected over here to the 1. This 1 is reflected to this 1. The 3 and the 3 and the 1. So it's 1, 3, 3, 1, right? 1, 4, 6, 4, 1. So once you get the first half of a row there, you're probably pretty good. You can double check yourself, but it better be reflective, right? So I better get a 4 and a 1. So the next one's 1, 5, 10, 10, 5, 1. Okay, so we see this lovely reflection. The only weirdness about the reflection is when there's an odd number of terms. Of course, I have this guy in the middle. I call him like the pivot guy, okay? And he's basically on the line of reflection, so he's not reflecting either side. So he's kind of like, I'm the guy you're splitting down the middle. So, but the reflective property, the symmetry there is really nice to know. The other thing that happens, there's actually a lot of people who have done a lot of research on this particular triangle. I don't know why, but it really captures people's attention. You'll see that, as I mentioned, this diagonal and this diagonal are always 1s. No worries, right? The next diagonals in, 1, 2, 3, 4, 1, 2, 3, 4. Okay, those are just consecutive numbers, and it makes sense because each time I'm adding this guy plus the 1 on the outside, right? So I'll just add 1, add 1, add 1. So those are consecutive numbers. But the really cool one comes in right here. The next diagonal in. 1, 3, 6, 1, 3, 6. And there's some other stuff that's in here, but those two are the really cool ones. If I had another row, like I just mentioned, the next row was 1, 5, 10, 10, 5, 1. The next number in this diagonal would be 10. So let me write that down here. That diagonal is 1, 3, 6, 10.